I can't reach that far. So you will have to understand that part, that this is not your lecture. You don't have to worry about that. It's, by the way, mechanics. The equation that you see up there, it's related to angular momentum. Does it look like what you're doing right now? No. A lot of calculus involved. All right. So we went over the definition of elastic collisions. So there are two types of collisions that we are going to go over: elastic collisions and inelastic collisions. What's the main difference? Say it again. Yes, yes. So inelastic one is the one where the kinetic energy is not conserved, it is lost in some form, and the other is the elastic collision where the kinetic energy is always conserved. So it's the two things which are conserved. For elastic collision, momentum is conserved, linear momentum is conserved, and the kinetic energy is conserved too. Where does that energy go? Sorry? Yeah. Which form? Some other form, right? It is gone into something else. Maybe it has changed completely into potential energy, because remember, we are not talking about the total energy of the system. We are not saying that the total energy of the system is not conserved. Okay, it's always conserved, the total energy. So what we are saying is the kinetic energy is not conserved. It has converted into some other forms. It could be potential energy, it could be some other form of energy, maybe gone into chemical energy, or heat energy working against friction. So friction is not the only example you could use for the kinetic energy loss. What you are saying, it's not the kinetic energy anymore, it has just changed into some other form of energy, and it could be any form of energy, including heat, potential energy. In fact, there are a lot of problems that you will do for the inelastic collisions which are related to kinetic energy going into the potential energy, but the total energy of the system essentially remains constant. That does not change. Kinetic energy can change its form, but the total energy still remains the same. So that law is not broken when the kinetic energy is not conserved. Now, we went over the definition, ideal example of the collision. We talk about elastic collision. Elastic means kinetic energy, whatever it was before, it remains the same afterwards. It has not gone into any other form. Potential energy, heat energy, there is no friction involved, there are no drag forces which are slowing down the system. It has remained the same. It's the ideal type of collision. Most of the atomic collisions, they can be considered as elastic collision, but in everyday life, rarely there is a collision which is considered as the elastic collision. One example, actually, we have you might have seen it as a child or somewhere, Newton's cradle. That is considered as a very good example of elastic collision. If you pick up one ball, it will pick the same ball from the other side. And it will, even though we call it an elastic collision, but you can hear a sound. That is also the energy it's getting from the kinetics of, it gets some energy from here, that's a kinetic energy. It gives it through these balls to this one, and that also moves. However, it does not continue forever. And we know that. Why? It's losing energy. Finally, it comes to rest. What happens if I pick two balls from one end? Two other balls, exactly. Is it possible to accelerate just one ball with high enough speed? Well, oh my God, that's always my fear. They get tangled. And do you have this at home? No? I do. My daughters bought it. So it will pick exactly, in order to conserve momentum and kinetic energy, it will pick exactly 2 balls from the other end. What happens if I pick 3? Oh, yes. Looks like you have worked with it before. No? Never? Oh, okay. Yes, the center ball will switch the roles. Okay, so center ball, in order to conserve the momentum, it will stick to the other side, then this side, and it's trying to conserve the mass and the speed. If there are no frictions, there is no heat, there is no energy lost in some other form, it should continue on like this forever, but it does not, because there are resistive forces here. So the one example, mathematical example for elastic collisions, I gave you 3 equations that we will use for solving the elastic collision problems. I'm not going to give you a total problem that you could read, but I'm going to give you the numbers. So there are 2 balls which are moving in opposite direction. One is moving with the speed of 30.0 meter per second. There is another one which is moving with the speed of, both have mass m, and it's moving with the speed of 20 meter per second. They both are moving in opposite direction. They collide with each other, they move away. Okay, just like these balls. However, since one of them is bound, they all are bound, so they cannot go anywhere. So their speed remains the same, but here they are not bound. They come into contact with each other, and then they move away with some speeds. Now we know that what is V1I for first ball, initial speed is this. For second ball is 20, by the way, it's 2I. And V1F and V2F are unknowns. And it's given that it is the elastic collisions. Now, since they both have the same mass, so it's not possible that one mass, if, for example, if one of the mass is really heavy, this one is really heavy, this is moving, it's moving, coming towards it, it's possible that this is bounced back from it if this one is too heavy. That is a possibility too, right? And if one of them has a lighter mass, the lighter one will move faster after the collision, the heavier one will move slower after the collision, and they will balance out the momentum same as it was before. However, they both have the same mass. Okay, they both will somehow going to exchange their velocities such way that the momentum is conserved. Now the equations, which equations we are allowed to use? Mm-hmm. Yes. So we can use the using the law of conservation of momentum. We can use the momentum before, momentum after, set them equal to each other. We can use the kinetic energy before, kinetic energy afterwards. We can set them equal to each other. We can also use the relative motion. We are allowed to use all 3. However, which one do you think is the most complicated equation to work with? The more complicated mean mathematically, which has more constants, variables involved. Which one is that? Sorry? The kinetic energy one. Because it has squares. First of all, it has squares, right? So it is possible you end up having a quadratic equation somewhere because of the square. there are m involved. So that equation looks like the most complicated in this category. The first one, the momentum one, and the relative velocity one is the best one, and the linear momentum one is also really good. So I will start with the relative velocity one, then I will pick momentum one, and I will see if I need more, then I will go for kinetic energy equations. Okay, even though you have to start with the relative motion one. So we know that the relative motion of the object with respect to each other is opposite to their relative motion afterwards. Correct? By plugging in the value 30 meter per second minus 20 meter per second is equal to minus V1F minus V2F. Looks good? Since they are velocity, we have to put the negative sign with it because it's moving in the towards left. This would give you 50. I'm not writing the units anymore. If you want to keep them with it, that's fine. Minus V1F minus V2F. That's one equation, okay, which tells you you are subtracting two velocities, and that is giving you a number 50. I'm going to use the second equation, which I find the most convenient one is the linear momentum. Linear momentum one is m1 v1I plus m2 v2I equal to m1 v1F plus m2 v2F. Now m's are all the same. They will get cancelled in this case. So I'm going to take away all the m's. v1I plus v2I equal to v1F plus v2F. Everyone understand why m are gone? Okay. Now we need to solve these equations. So these two are given to us, right? 30 minus 20, v1F plus v2F. That gives you 10, v1F plus v2F. Now you got two equations. Now you have two equations. Do you think you can, how many equations do you need to solve for? So what we are looking for is the final velocity of first ball and the final velocity of the second ball. So how many unknowns are there? 2. How many equations do you need? 2. You don't even need the third equation. All right? If there are more unknowns, yes, you will have to go for the third one too. So can you solve these two together and get the answer for V1F and V2F? It's very, very easy to solve these two equations. One of them will cancel out. If I add these two, I get, if I add them, V1F get cancelled. So it gives me 60, V1F is cancelled, plus 2 V2F. V2F is equal to 60 divided by 2 meter per second. And what would be V1F? V1F minus 20 meter per second. Sorry? So when you add these two equations, this and this, so V1F is negative in this one, V1F is positive in this one. They cancel out. And V2F is positive, V2F is positive here too. They add up. So that will give you, basically you have just added equation 1 and 2. So adding 1 and 2, V1F cancels. Sorry? Two equations? By doing this. Algebraic addition. This will, left hand side will be added together, right hand side will be added together. They both are positive, these two get cancelled. These two, this, so when I multiply this negative sign in there, that becomes positive too. So if I take this away, this would be positive. They add up, that gives me 2 V2F, which is on the right hand side, this gives me 60. Good? How difficult is the problem on the scale of 1 to 10? It's quite simple for elastic collision. Did we know the answer before we started? Yes. How? Janelle, right? Did they switch the energies? They switched. Why? Okay. Yes, they are conserving the kinetic energy. Yes, it is elastic collision. Why the energy exactly got switched? Because they both have same mass. Right? So the only way they could conserve the momentum and energy, they switch their velocities because they both have the same mass. It is not true when the masses are different. Okay? If you had two different masses with the same problem, one 20 kg, one 10 kg, all right, they will still conserve the momentum, they will still conserve the kinetic energy, but they can never move with the same momentum because in that way, same speed, because in that way they are not going to conserve the momentum. This is going to go with the smaller, so they will basically combine their speeds, correct, and they will take the chunk of the velocity according to their mass. The heavier one will get less velocity, the lighter one will get more velocity. But at the end, they both should add up, giving you the same momentum. So this is the simplest example that you can see. It's the most important thing is, for me, is for you to understand how to put the equations together. What are we trying to get out of them? Okay, elastic collision problem are always like that. Something will be missing there. You just have to play with the equations. They will be a little bit more complicated if you have the masses given there. And masses will be different. Okay, that would make it a bit more challenging for you. If a mass is missing, then you may have to work with a third equation, because then there would be another unknown. Make sense? All right? So, putting the equations together, and this is the elastic collision problems. You can use the relative equation. I don't know if somebody has missed that point. We could use the equation number 3 here because it was the elastic collision. We were not allowed to use it for a non-elastic collision or inelastic collisions. Let's look at one problem which is not elastic. Do you remember the projectile motion lab? where you mounted the ball on a machine, then you let it go, it goes in a trajectory, projectile, in a curve path, and you calculated the initial speed. You remember that lab? Do you remember there was something hanging in there in the center which looked like a pendulum? It was movable. You got it out of the way because you were not using it. Does it ring any bell? It looks something like this. A pendulum, and there was a place, a cylindrical shape under it, and you had the ball mounted at the end here, which is ready to go. You got this thing out of the way because you just needed the projectile. But if it is hanging on the way, so now consider the situation when this pendulum is, big pendulum is on the way and its mass is given as m. The mass of the ball is small m. What happened there? What happens when this ball is released? It's going to go, hits the pendulum, it gets stuck in it. Okay? When it gets stuck in it, so the next position would be the ball is in it, inside. So the total mass of this whole thing becomes m plus m when the ball is inside that pendulum. Basically, that pendulum is there to catch the ball. All right? The mass has changed. Yes. Is it elastic collision or inelastic collision? Will little m come to rest? Yes. Will big M be rest at the moment? Yes. Yes or no? For the moment? Okay. Both have come to rest. Sorry. Big V, the velocity of the big pendulum is 0. This is a beautiful example of inelastic collision. This ball has completely lost its energy inside. V goes to 0. It comes to rest. It moves with the basically whenever two objects combine and then they move together. Perfectly inelastic collisions when two objects stick and move with same speed. This is an example of perfectly inelastic collisions. Okay, that they have lost the kinetic energy. Kinetic energies cannot be the same for both masses sticking together. Masses must have lost the kinetic energy in order to stick together and move with the same speed. Now this applies to this. When this ball gets stuck with the big pendulum, they are together. So this inner ball has completely lost its kinetic energy, given it all to this total mass. What do you expect next? They will move because it's a swinging pendulum. It's free to move. This will move. It will rise and it will get stuck at some height with that little ball in it. Now in the picture it looks like they gained size too. This is the zoomed in version of the same thing, so you can see it better. The height has changed. It's h1 initially, h2 finally. What kind of energy it has at the top?
At the top
When it is swinging, going up, what is it doing? It's losing its kinetic energy, and it's gaining its potential energy. Kinetic energy has completely converted into potential energy at the end. So at this point, this has the potential energy maximum and the kinetic energy is 0. At this point, potential energy is not started yet, but kinetic energy is maximum, but a combined kinetic energy because they both are together. Now let me give you some numbers. If M is 5 grams, big M is 1 kg, and initially it has gone to a height of 5 centimeter. There are 3 pieces of data given. Big mass, delta H would be 5 centimeter. Okay, 3 pieces of data given. Mass of the ball is 5 grams. So the ball which is being fired into the pendulum is 5 grams. The big pendulum is 1 kg. It should be heavier. And when they are all together, at the height it has reached up to 5 centimeter. You want to know what was the initial speed of the ball. Okay, let's do that later. First do the system. We can get it later. V system means the ball plus the pendulum. All right. Can someone tell me which speed are we specifically looking for? Where in the motion? This is V, small v, big V is 0 here, and then they move together with a common speed which is V system. We are looking for the speed at the center when they got combined, where it was all the kinetic energy. So how do we find that? Now, we can use the energy at point. Let's call this point at O. This is A. So the energy at point O should be equal to the energy at point A. Correct? Right? Should be true. So energy at this point same as the energy at this point should be same as the energy at this point. So I'm comparing two of those from position this and this. So energy at O is kinetic energy plus potential energy. Energy at A is kinetic energy plus potential energy. Now kinetic energy is at the center. What mass I should use at the center? Little m, big M, both. Both. V system square plus, what about PE? 0. Because the height is 0, no change in position. But what about the kinetic energy at point A? it has come to rest, 0. Potential energy at point A, that cannot be 0, right? Because that would just take all the meaning away from the equation. Where this kinetic energy going to? It is going to m plus big M combined mass G delta H.